You may need to click OK. Well, okay, welcome to another Institute for Astrophysics of Andalusia seminar series. On this occasion, we have Alejandro López-Vázquez, and Guillem Anglada will make the introduction for him. So please, Guillem, go ahead.
It's a pleasure to introduce Alejandro López-Vázquez. Alejandro got his PhD at the National Autonomous University of Mexico. His thesis advisors were Jorge Cantó and Susana Lizano, two of the most important theoreticians living in star formation. Jorge is an expert in hydrodynamic for the interstellar medium, and Susana is an expert in magnetic field. After his PhD, Alejandro did a short postdoc also at the National Autonomous University of Mexico, at the UNAM. Then he was teaching for a couple of years at the National Technological Institute of Mexico. And since 2022, he is at the Academia Sinica Institute of Astronomy of Astrophysics in Taiwan. It is the ASEAN IAA. And his PhD thesis was on the role of the angular momentum in the infalling material that forms a star. And now he's working in the outflows that are associated to the protostars. But interestingly, he now is working both in observational data, he's using ALMA data a lot, and also doing this theoretical modeling of the outflows. This is a very interesting approach. I would like to stress the importance of the physically self-consistent modeling of the observations. In galactic astronomy, we have the opportunity to do physics and not only statistics. So it's very important to understand the physics and the role of people like Alejandro, who knows both the observational techniques, so the problems, the artifacts of the observations, and also knows the equation that drives the processes. Is very important, this mixture of in the same person. Today, Alejandro will talk about the multiple components in the protostellar system, H212, and the floor is yours.
Okay, thank you very much for your presentation, Guillem. So for me, it's a pleasure to give a talk here because I come back 5 years ago to the institute, to Granada, and it's a very nice city and very nice institute. So I am very happy for being here. So, okay. Today I am talking about the protostellar system H212. So this protostellar system is very new, so it's very well studied because this is the advantage with the other objects because the axis of the jet is perpendicular to the line of sight. For this reason, we can observe the multiple components like a outflow, jet, envelope, also the disk. So this is a very famous object. So in the context of the star formation process, the star born in a molecular cloud for different physical process could be collapse, could be. So including collapse, including magnetic diffusion, including a lot physical process. So when we have the protostellar system in the center of the cloud, start to the accretion material to the protostar. So for the angular momentum conservation, forming a protostellar disk, and also start to launching material from the poles of the stars in the different forms. Could be the very collimated and high velocity component. This is named to protostellar jet, and also you can observe the molecular outflow. The difference is the emission because the protostellar jet usually emits in the atomic, could be atomic emission, for example, iron, nickel, and also observed in the optical wavelengths. And respect to the molecular outflow, the name say is molecular emission of the SO, CO, and other molecules like a CS, and it's a variety of the different molecules. So also the difference is the jet is collimated and the outflow is present the opening angle, a wide opening angle, and is slower than the jet because the jet present velocities around the 100 to 100 kilometers per second, while the molecular outflow presented 10, 20 kilometers per second in the velocity in the direction of the expansion. Also, the envelopes is very important because the envelopes, you can see in particular in the class 0 and class 1 objects, is where the protostellar system obtain material, because we have in the system, we have the envelope, and the envelope accretes material to the disk. So in the disk, accretes material to the star, forming planets and launching the jets and outflows. So these envelopes, the classical models say that, okay, start to particle and follow radially to the disk. However, if these envelopes present rotating velocities, so the trajectories change. Also, we have the specific size. Also, this change the trajectories. So these trajectories named to accretion streamers, and in this protostellar system is very nice because you can observe the outflow with the red shifted emission and blue shifted emission, but also you can observe the accretion streamer. This streamer start the particle in the boundary of the cloud and start to follow to the accretion disk and feed the accretion disk, eventually different process in the protostellar disk and launch material. So this is the envelopes also for the angular momentum conservation. These envelopes tends to forming a flattened envelope. So like a toroid. How do you say toroid? Because also present a rotation velocity. So you have the outflow in the different direction, in the north to south direction, and around the outflow, you can observe this envelope. And this envelope is rotating. And this rotating fits the disk, but in this cartoon is very nice because you can observe the outflow, you can observe the envelope, and this is the streamers. This is the accretion streamers. These accretion streamers feed the protostellar disk. The first evidence of the accretion streamers was detected by Shiwei in the L1489 object, and the streamer evidence you can observe like a tail between. You have the very well-defined disk, and you can observe the tail. Also, these streamers are detected in the high mass protostellar systems. For example, in GGD27, in a paper of the last year, so we modeled the different accretion streamers detected in the metalon emission, but also detected in the other tracers, like a formaldehyde, the CS, and the more complex molecules. So this is the first stage of the star formation process. The envelope accretes material to the disk start to rotating material, forming planets, but a very characteristic of process in the star formation is the launching of the material. So if we have a very high rotation velocity in the disk, it's necessary to remove the angular momentum. Because when removing the angular momentum, so you can form planets, you can form the star. So the best candidates to remove this angular momentum is the stellar winds and protostellar jets. So how do these winds removing angular momentum when the particle is anchored to the magnetic field lines associated with the disk. So in this case, we have you can imagine like a dot or a ball, and the magnetic field, you can imagine like a line, so for this reason, is rotating, the system is rotating, the magnetic field also is curved, and it start to particle in a specific point. The particle follow with the magnetic field until the Alden surface. The Alden surface is where the radius is launched. For the reason you can increase, you can have the different launching radius. In this case, we have two different theories. The first one is the X-wind. When you can observe in this cartoon, the X-wind say that we have the magnetic field of the protostar, and the protostar truncates the disk in this point. In this point, the disk cannot rotate because it's truncated by the magnetosphere of the star. In this point, this point, the wind is launched in all directions. Could be very vertical. This is the jets, and also could be with very radial velocity, with very radial opening angle, and interacting with the envelope and forming molecular outflows. Other explanation is that this wind could be launched from the different region, So the launching radii could be bigger than the X radii, because this is the X radii, the X region. X wind say that, okay, the wind is launched in this point, in a specific point, or in the other, this wind model say that no, it will be launched from a wider range of the radii. How I said that the stellar winds and jets are launching directly from this. So the molecular outflow usually are described by a suite of material. So we have the wind, we have the jet, and interacting with the envelope, with the cloud, and forming the molecular outflow, because the molecular outflow is the entrained material from these very fast stellar winds. So the different models, for example, was discovered in the 1980 for Snell, and Snell say that the molecular outflow is a very fast stellar wind, collision with the envelope, and forming like a very thin shell. So this shell is a molecular outflow. Obviously, in this stage, don't have the resolution for distinguish this specific shell. Also, Xu in the 1991 modeling the same. So this they say that, okay, we have a stellar wind in the center, is launching from the central star and producing a shell because the environmental material is static. The difference in my PhD thesis, I developed the semi-analytical model when I study the same interaction, the stellar wind launching from the star, but the difference, I included a rotating envelope in collapse, rotating cloud and in collapse. So including the rotation velocity and obtaining the molecular outflow for different stage is very specific shell. So this is the main cartoon or the main models to producing molecular outflows. But also we can distinguish in two different ways. Could be the bow shocks and the wide angle winds. In the bow shocks, the people explain the molecular outflows because we have the jet, and the jet is very fast. The jet interacting with the ambient media and producing like a bow shocks. The bow shock is like a, I cannot explain it. This is a bow shock, like an arc. And in this arc, in this bow shock, the material slides to the sides and forming different shells. For the reason you can observe this characteristic shape, and it's associated with the molecular outflow too. And wide angle these winds, we have a wind with a very high opening angles and interacting with the ambient media. The characteristic of this model is if we analyze the position velocity diagrams along the jet axis, you can observe like a parabola shape, while the perpendicular to the jet axis, you can observe like an ellipse shape, like you detect the shell of the molecular outflow. In a recent paper of the CNH hand, she unified both models. So they consider that the wind is launched from the central part consistent with the X-wind scenario, and the wind is launched interacting with the ambient media, and consider the different physical effects. For example, Kelvin-Helmholtz stabilities, perturbations in density, in the velocity, in the magnetic field, and they produce the both shapes, the bow shock and the wide angle, the characteristic shell, external shell of the molecular outflow. So they, for example, this is the forward shock, this is the external shell, and the difference on the bow shocks, they don't consider that the jet pushing the material. So they consider that this is instabilities eventually reconnecting. And for this reason, you can observe the bow shock shape. And in these plots, you can observe the shape of the molecular outflow producing by this model with unified both ways. So the recent interferometric and infrared observations, you can observe these very high details in the molecular outflows. The first one you can observe the multiple shells. In HH46, 47, you have an external shell, probably producing by the interaction between the wind and the ambient media, but also have the internal shells. This internal shell probably is material launching directly from the disk and forming by perturbations in the velocity, in the density, and producing a forward and inner shock. This shape also is observed in digital V, in the position velocity diagrams, and also is observed in HH30 when we detect that the external shell and two internal shells, but this internal shell is lower than the external shell. So don't reach the external shell. Other characteristic is that in the molecular outflows, we can detect the gas is rotating, or the gas percent gradient of the velocity interpreted as a rotation. So this is important because if we assume that these winds extract the excess of the angular momentum from the disk, it's mandatory that we observe this rotation velocity. So in the molecular outflow, for example, in PMC1, you can observe the blue shifted and the red shifted part. Also in the NGC 3033 or Orion Source I, this is a massive protostar, very, very massive protostar, or also CB26, when observe a blue shifted and a red shifted velocities, interpreted as a rotation. And with the recent very high observations and the James Webb observations too, we can detect that the outputs present an onion structure, onion-like structure. The onion-like structure is we have the different shells of the different material. For example, with the observation of ALMA in 2022, the people detect that this is the SO emission, and in the green is SIO emission. We have an external emission of the SO and internal emission of the SIO. Also is detected in digital V. In digital V, with the comparison between the ALMA observations and the James Webb observations, this is the external shell of the CO. Internal to the CO, we have the emission of the H2, or dispersal light, and in the center, the jet is very, very collimated, present very high velocities. And 1 week ago, probably, of this month, in HH46, 47, also present the same shape. The CO, the H2, and is the same shape to the onion-like structure. This onion-like will be a spatial and velocity structure. And the HH212 is a very, very famous protostellar object because the distance is located in Orion. The distance is around 400 parsecs. And in this part, you can observe the SIO jet and the continuum envelope. If we focus in the other molecules, the CS traces the interaction with the envelope, with the jet and the outflow. So in these maps, I present the emission of the HCO plus, and you can detect the interaction. The low velocity traces the interaction of the outflow. The outflow is traced with a different part, the black lines, and traces interaction with the envelope, while the high velocity emission of the HCO plus traces the flattened envelope. So this say with more detail in this image. Low velocity, the interaction, and high velocity, the flattened envelope. Like a toroid is a very. Also, this object is very famous because present a edge on disk, a dusty disk, when you can observe the atmosphere. And the atmosphere is very rich in the in complex molecules, like a methanol, like a CH2DOH. So a very high, very high complex molecules. If we focus in the emission of the outflow and the jet is traced in green with the emission of the H2. You can observe the different nodes. Also, you can observe that the jet is processing. In this part is processing. And in red is the CO emission. The CO emission traces the molecular outflow. And you can see like the potion is connecting with the molecular outflow. For the reason that people interpreted that this outflow is very consistent with the potion model, when the jet interacting, pushing the material and sides the material. It will focus in the central region. We detect the SIO jet, and this is very important because it's the first jet when we can detect the rotation velocity in the nodes. So I mentioned previously that the molecular outflow, you can observe the rotation velocity on the gas, but in this case, the nodes is rotating because you can see the pattern between the blue shifted and red shifted velocities. So in this object, the new results, we're exploring the emission of the H30CO plus. And if we compare with the HCO plus, the HCO plus traces the higher velocity respect to the velocity of the system, while the H30CO plus emission traces the low velocity components. And in the channel maps, you can observe that the velocity is very close to the systemic velocity. You can observe all envelope, and for higher velocity respect to the system, you can observe the red and the blue shifted component. In the emission map, the shape, in purple contours, you can observe the HCO plus emission. HCO plus emission in general traces the interaction with the outflow and with the envelope. It's like a wall, it's a boundary of the outflow. If we observe the emission of the H30CO plus, you can observe like a toroid around the molecular outflow. And in the velocity maps, confirm that this envelope is rotating. So this is in contours, a very small contours. You observe the emission of the HCO plus, high velocity, is a flattened envelope, but you have also in the envelope could be interpreted that we have the differentials, a shell of or a very small envelope traced by the HCO plus, and a bigger envelope associated with the H30CO plus. So if we explore the position velocity diagram along this midplane, you observe that the position velocity diagrams, we cannot explain like a Keplerian rotation, and also I cannot explain like a angular momentum conservation, probably including both effects. So along the jet axis, you observe the infalling movement, the infalling velocity, radial to the central star. So if we exploring with more detail along the major axis, that in this case is this midplane, if we consider the cloud, a molecular cloud with a specific size, and this cloud is rotating, and this cloud is in gravitational collapse, we can producing the trajectories. And this is the blue shifted velocity, and this is the red shifted velocity. And the observer is in this position, in x equal to 0. So if we're producing the position velocity, the position velocity diagram, we can explain, it's very consistent. This model, we consider all movements, the collapse and the rotation, is very consistent with the position velocity diagram. So in the case of the molecular outflow, we only focus in the central region because we're exploring the ALMA observations. In this case, we use the 3 different data sets in order to obtain a very high signal to noise, we're combining 3 different data sets. And the talk is focused on the CO emission, but also I refer to the SIO and SO emission to comparing our results and comparing the structure of the protostellar system. So this is the low resolution observation of the 3 molecules, CO, SIO, and SO. The low resolution is around 0.5 arcseconds. And you can observe the external outflow, the internal jet. This part is in blue. It's like a outflow, probably is the SO emission, and in contours is the continuum emission of this. But if we explore it with high resolution, you can observe with a very high detail the external nested shell reported previously. So with the CO, also the disk present the atmosphere. So the jet is tracing with the SIO, sorry, and the SIO you can see the jet internal part, the different nodes, and also tracing the external shell. In the SO, you can observe that we have the external SIO shell and CO internal material. And if we explore more detail and comparing the CO with the SIO, this is the jet, the knots, it's very nice knots, the external shell of the SIO, and also external nested shell of the CO. And if we compare with SO, both tracers coexist. We can assume that will be tracer this country. So if only see these observations, it's clear that you can observe the external nested shell, the magnetohydrodynamic, this wind, the wind contained to the SO, and also the protostellar jet. For this reason, exploring the CO emission maps only consider the blue shifted emission, traces the north of the part, and you can see the different points, very specific points. This could be traced with traces the CO knots too. So the CO also traces the jets. So in the red shifted, also you can observe these knots. So these knots aren't observed in the total intensity map, but if we do a zoom and consider only higher emission, a very high signal to noise, we detect until 10 different CO nodes. So the CO traces the external shell, the magnetohydrodynamic this one, and the jet too. If we're exploring the nodes is expanding, presented radial expansion. This expansion, if we compare it with the SIO, the people has a very high resolution observation. But if we compare it also increasing, it's not too, the line present a slope that is increased, but it's not very high increasing. So probably this expansion of this node increase the width with the height or with respect to the distance to the central star, probably because present a sawtooth pattern. This considers that we have a node and the node is present a radial expansion, and eventually this node forming a bowshot and in the material slide to sides. But we cannot confirm because this pattern you can observe if we have a very high inclination angle respect to the the plane of the sky. In this case, this object is in the plane of the sky, it's perpendicular to the line of sight. Also, this outflow is rotating, present a very high, very nice redshifted velocity and blue shifted velocity. If we do a zoom, so if I'm comparing with the SO emission in contours, traces the same pattern. So the SO and the CO traces the same region. Also tracing the rotating outflow. And in order to confirm, we did the position velocity diagram along the jet axis. And in this position velocity diagram is very interesting because we have the external SIO shell. In this part, this is the jet, but this is the external SIO shell. Probably is free wing gas of the CO because the CO is contained into the SIO shell. And the SO, this we have the molecule, the SO don't have emission. No, the observations don't covers all emission of the SO for the reason is called here. But you can infer that present a very typical parabola shape of the disk. So also this parabola shape connecting with the SIO shell. Probably in this case is connecting. This is connecting. Probably the CO is pushing the SO and the SIO and connecting and forming this shell. Also, if we consider the position velocity diagrams perpendicular to the jet axis and far away to the central source, observe this onion-like structure too, because we have an external nested shell that presents a very low velocity. The SIO expanding shell inside the SIO also observe the SO, and the CO in gray scales present a contained gas, a free wing gas. So if we consider that this is a free wing gas, we expected that the gas present very high velocities, very high velocity expansion, around 100 to 200 kilometers per second. However, if we consider that the outflow is in the plane of the sky, it's very complex to measure this velocity because the velocity is in this direction, in the jet axis direction. It's very complex to measure this velocity. The error bar are huge in this case. So if we analyze the region central to close to central source, we observe that the CO and the CO is in gray scales and the SO is in blue scales, coexist, traces the same region. So in velocity, in the spatially traces the same region. For this reason, we can assume that the CO also is tracing the magnetohydrodynamic in this way. So, and this ellipse shape is associated with this root, and you can measure the different kinematical properties with the characteristic of the ellipse. For example, if we assume that the CO is launching directly from the disk in a very specific ring, and this ring is launched, and you can measure in this cartoon, you can observe, you can measure the zeta velocity, the velocity field, the cylindrical radius, and it's associated with the parameters of the ellipse. For this, use the model of the Fabian-Lobet and assume related the parameters of the ellipse with the velocity field of this wind and with the position of the disk wind. For this reason, we obtain the cylindrical radius, and you can observe that the cylindrical radius increasing with the height, but tends to a constant value. Probably this constant value is because the SIO is slowing down the material. We have the SIO shell in a very specific position, probably it's slowing down. And this effect also is observed in this region of in the expansion, in the radial velocity, expansion radial velocity, because tends to a constant value. Probably reach to the SIO shell and start to moving together, both guys, the shell and the CO gas. the rotation velocity is decreasing. This is expected. And finally, the angular momentum, the specific angular momentum, tends to a constant value because the rotation velocity decrease and the radius increase. For the reason, you can observe that like a constant angular momentum. So like a summary in this cartoon, we can observe the different components of the molecular outflow or the protostellar system, because we have the envelope, we have the accretion disk, the material infall to the envelope to the disk. So in the disk, this point is the X wind, and the X wind is launching in all directions, but they're very specific point. We have the knots, and the knots interactive, forming the bow chokes, and this is the CO gas. This is the this wind. This shell probably is forming by the interaction between the X wind with the this wind and forming this SO shell, SIO shell. And this is this wind when you can observe the redshifted and blue-shifted velocity, and this external nested shell is forming by this wind or stellar wind with the envelope, the interaction with the envelope. If we acute in this direction the position velocity diagram, also observe the external nested shell, very well defined, the emission of the envelope, and the container gas or the free wind gas, and the SIO shell. While if we do the position velocity code close to central disk, we observe that this wind, when the redshift and the shifted velocity, the emission of the jet, the jet present a very high velocity. For the reason it's very small, but with a very high velocity dispersion. The external nested shell, however, don't have an angular resolution, and the emission of the envelope. So what is the origin of the magnetohydrodynamic disk? So if we do a different assumption, for example, that the wind is free. So free is that non-interactive with other components. This is a very is complex to assume this. In this case, we can assume that the external nested shell and the SIO shell is a very high radiative. For the reason, the old material don't interact with nothing. So the other assumption is that the wind is very cold. For the reason we can know including the entropy effects, and also it's axisymmetric. In this case, we can use the Anderson relation when related the velocity in a specific point with the related specific point with the launching point, and the velocity of the outflow, the rotation velocity, the expanding velocity, the poloidal velocity, all components, and also including the characteristics of the central star. Here in eta parameter is the mass of the central star, the gravitational constant, including the characteristic and the rotation velocity, and this where it's located. If we assume this, we obtain that the launching radius is between 4 to 8 AUs, consistent with the wide angle these wings, and consistent with the previously reported by Pascucci for the class 0 objects between 0.3 until 4 AUs, and also is consistent with the value reported previously by Benoit and Xinfei, but they obtain these values through numerical models. And this is observational analysis and consistent with the expected to the theoretical models. And the other important parameters in the magnetohydrodynamic disk winds is the magnetic torque, the lambda parameter, very well also known like a lambda parameter. This torque indicates how is the quantity of the angular momentum extracted from the accretion disk. If we assume that the jet and the stellar winds removing the excess of the angular momentum, we expected that the lambda value is higher or is big, because this is a very efficient magnetohydrodynamic disk winds to extract the angular momentum. So, and we obtain the angular momentum is between 3.5 and 4.5, and also is consistent with respect to the numerical simulations that is between 3.5 to 5.5. So this object is a very nice protostellar system because we can observe that the wide angle wind and jet driving wind would be coexist, so are not excluding. So in the unified model also can explain these molecular outflows because we have the vultures, we have these winds, we have everything, and all components are decisive in the evolution of the star formation process. Finally, like a summary, so the system presents a very well-defined and on like a spatial and velocity structure because we have the different shell, we have the different components, and in a very specific position and with a very specific velocity values. Also, we detect that the CO like a this wind tracer and is consistent with the SO characteristics. And additionally, or finally, so we detect probably the free wind gas inside the SIO shell. For me, it's all. Thank you very much.
Thank you very much, Alejandro, for this nice talk. Are there any questions, Mayra?
I am fully agree.
Yes.
I like too much the presentation.
Okay, thank you.
I had many questions, but I am.
For the microphone.
Okay. Yes. A new ingredient in the star formation paradigm, of course, is the streamers. Do
Yes.
you know is there evidence that the mass accretion rate is higher in these streamers or tails than in other branches of the system? And the second question is something that attracted my attention is the rotation in the nodes. Do you know which is the reason? What we can explain the rotation of the nodes ejecting in the interstellar medium because of rotation of cities. I am wondering about the possible mechanisms to explain the kinematics further like the outlook that you have presented.
Yes, okay, thank you. So we can distinguish the rotation velocity. Okay. Oh, probably in this image. Let me know here. In the protostellar jet, we can assume that the rotation velocity is because the material is associated with the magnetic field, and the magnetic field could be helicoidal. But this is in the case of the jet, only in the jet, because in the jet, we have an ionized gas, we have an ionized, for the reason you can follow the magnetic field. However, in the molecular outflow, it's very complex because the magnetic field is very weak and we cannot explain all material very far away to the jet axis. In this case, I think that the wind could be launched in a very specific point and follow the straight line, but the straight line is in the space. So we only observe the plane, but if it's in the space, for example, in this point, you can launch it and you can observe like, this is the blue shift, the red shifted, or in the other case, this is the blue shifted. Could be an explanation. But is that it's launched with the magnetic field, but the magnetic field very far away to the central star is very weak. It's complex to explain the rotation velocity only by the magnetic field. Could be more effects.
Is this the only case where we can see rotation in the nodes?
Yes,
Because,
if I remember good, it's the
because there are another molecular approach with rotation, but
Exactly.
not in the nodes. No?
yes, exactly.
Well, if I can comment, I think that is digital that also presents rotation in the jet.
In the jet, yes, exactly.
I think. And that was the first, I think, in 2004, something like that.
Yes, but it's
Pachotti, Coffey, all these people.
yes, exactly. But no in the node. I remember that
These
paper-
were very close, right?
very close and the jet is rotating, but don't have no angular resolution to distinguish the knots
Right.
in the digital beam. Exactly, that's correct. Thank you.
Until the
So again, thanks for the talk. I wanted to ask if you have an idea of the time that, so time lapse between consecutive nodes.
Okay. In this image. Oh, for detecting the knots, I did the yes, I did a proof and obtained the spatial profile. And the all knots is associated with the emission over 15 sigma. So we have a noise of the image and we can observe the peaks of the emission. And for the reason, assuming that these peaks is associated with one notch. Oh, this is the question, or?
Well, my question was more, how much time? So.
Oh, the dynamical time.
Yeah,
No,
yeah.
I don't know, sorry. It's complex to measure the dynamical time because if we consider that we have the SIO shell, probably it's a low one. Also, the dynamical time is necessary to measure the velocity in the theta direction, in the jet axis direction. And given that the molecular outflow and the jet is in the plane of the sky, these measurements probably has a error bars huge. Probably between, if I can measure 100 plus minus 19 kilometers per second. It's very complex.
Okay, so the second part of my question
Yes.
was that I asked this because I will guess that for objects in different stages of evolution, I mean, comparing these different objects,
Yeah.
maybe we can find different time lapse between nodes if they are, as I understand, related to the accretion events.
Yes, probably. For example, this is class 0, and in this class 0, you can observe a very high we can detect a lot components. The accretion rate is very high, but if we compare it, for example, with the HH46, 47, this is class 1. And in the class 1, the shells are very well defined. And if we compare with this HH30, H30 is class 2. And the class 2, in this case, we didn't observe the envelope, we didn't observe only observe the molecular outflow and the protostellar jet. And in the protostellar jet is weakly, present the weakly movements, and also the knots, but very well defined knots.
But are not the proper motion
Oh, yeah.
measurements in
HH12?
H.
Yes, I didn't remember. I don't remember. Sorry, what is the number of the proper motion, but the people measurement the proper motion in the notes.
Because when you have a jet in the plane of the sky, you cannot measure the line of sight velocity, but
Yes.
you can measure proper motion. This is the
Exactly.
opposite when you have a follow-on jet, for example.
Exactly.
So it has this advantage of being able to measure proper motion. So
Yes, and also
you can have an estimate of the dynamics of times.
exactly. Yes, and also the jet probably is processing. With the proper motion, the people measure that the jet is processing too.
Well, thank you very much, Alejandro, for the nice talk. It's been wonderful. I have another question, but I guess a big one is that do you see any kind of acceleration? Not in particular in H212 because it's in the plane of the sky, so
Yes.
it will be difficult with the radial velocity. But I mean, in general, in your molecular outflow observations, if you have any indication for acceleration with distance, like because this is also believed that it may happen,
Yes.
and I wonder if you see anything like it.
Yes, exactly. In the different molecular outflows in the position velocity diagram, when you can observe the parabola shape, if the parabola shape is associated with the gas is accelerating with the distance to the central stars.
Right, so I have a follow-up question, like,
Yes.
how do you accelerate molecules? Because I can understand that like ionic species like ionized iron or nickel sulfur, but how do you explain that?
A very good question. I don't know. I need to think because for me, it's a question always, why is accelerating? Because probably because in the central source, around the central source, you have the envelope, you have the other components. But if we follow the gas in a specific point, the density of the material is lower, and the gas could be behavable like a free gas.
Could it be then, like, if I go up, that this ionic or atomic component is dragging all the
Exactly.
molecules and also accelerates? I don't know. I
Yes,
just,
probably,
I've
yes.
been asking this myself 30 years, and I hope that you have that.
Yes, exactly. No, it's a very complex this part.
Okay.
It can be an apparent acceleration. I want to point out that if you have several ejections, episodic ejections, and you have some of them that are launched at higher velocities, and others that are launched at smaller velocities, when you make a picture of the full jet, you will find that the particles that move faster are far away than the ones that are slower. They are ejected in a range, let's say in a range of dynamical time. So there is this called the Hubble-Lemaitre law. And there is a tendency of finding the faster particles far away than the slower particles, in addition to any other interaction with the ambient field. So it can be just an apparent acceleration effect because you measure higher velocities at larger distances. Right? Does not necessarily mean that the jet is accelerating, but that simply, when you take a picture at a given time, you find the faster particles far away.
Okay. Yeah, thank you.
Maria.
Thank you, Alejandro, for the nice talk. Well, it's concerning precession, the precession motion. So my previous question was about precession, but you have tell us that the jet is precessing. And I'm wondering if the precession period is similar to the time scale in which the nodes are ejected, or there's some relation.
I don't know because then no, I don't remember. Sorry,
Okay.
but yes, I need to check the papers.
Okay. And another related question, it doesn't impact with your assumption that because I guess that you assume there is an isolated object launching the jet with
Yes.
launching region with its own disk. So if it's precessing, it might imply that well, it has a companion or
No, in this case, only detected the isolate star
okay.
because in this case, for example, we have a very high resolution observations and only detect a isolated star. Probably, but I don't know because it's edge on. Probably this could be cover all the stars, but it decided to the stars is very close 1 to 1 because the angular resolution, the higher angular resolution is in the continuum emission and the SIO emission in this case, and the angular resolution is around 4 IUs. It's a very high resolution.
Okay. So my question was it relevant for the assumption?
Yes, exactly.
I have another question, if I may. Right, about the launching radius.
Yes.
You quoted a few numbers there, and I wonder if that's a general radius for all the jet or the outflow, or does it change with the
Change
tracer?
the object.
You know, not with the object, assuming the same object.
Oh, the trader.
Same properties. Is it different, for example, from iron, like atomic species that can be traced with HSD or James Webb? Or is it the same as the one that you trade with the molecule, SIO, CO, etc.? Or how you know,
Change.
is
For example, for the SIO emission by the jet is consistent with the X-wind, and the launching radius is around 0.05 AUs. And the CO and SO is similar.
sorry, you said that the launching radius for the CO is 0.05 AU.
Yes, 0.05 AU.
And how can that survive? So close to the
Is
star?
the X-wind, is the X-wind model. And in this case, here, we detect that the CO is launching from the 4 to 8 AUs and is consistent with the same object, and the for Benoit and Chin-Fei measure with the numerical model, but is a SO emission. And so in this case, the SO and CO tracers have the same launching radius.
Right, but if you were to measure it to another tracer, you may
Yes.
find another.
Exactly,
Right.
because in this case, we can assume that the jet is launching from the X-wing,
Right.
X region, and the outflow will be launching from this one region.
Thank you.
But there is not a degeneracy between the magnetic lever arm, the assumed magnetic lever arm, and the launch radius, or you can fix both the
No,
two
it's
separately,
separate.
independently.
Independent. Because in this case, obtaining the magnetic lever arm, like a specific angular momentum, and the polar velocity. In the launching radius, I use the Anderson relation. So independent obtain the same values and consistent with the.
I had a question regarding the HH30 outflow. I only puzzled because you find the highest velocities at larger distances in the outer shells, I mean. So you
Okay.
find the inner shells move slower than the outer shells. So I have misunderstood something.
Okay, yes.
Because I will expect that the inner region will have higher velocities.
Yes, exactly. So this velocity is in the line of sight, not in the jet axis.
Yeah.
So it's slower, it's slower, the internal shell presents lower velocity, probably because we explain. So in this case, the higher velocity is in theta direction, in the direction of the jet axis, and the expansion, the radial expansion, present the lower velocity because probably it's slowed down by the other shells. Because this shell, the external shell, tends to a constant value. If you can see, then the external shell has constant value, constant velocity. And you can observe that the medium shell tends to reach this velocity, tends to a constant velocity too. And in the case of the internal shell with the height increasing, but also tends to a constant value too. For the reason, in the theta direction, present the higher velocity the internal shell than the external shell, while the index radial, all shells tend to
I would tend to think that the
yes,
radial velocity in the direction, the equatorial plane will be higher for the points that have been ejected from radii closer to the star.
Yes, exactly.
In one thing, in a Keplerian rotation, the points that are closer to the star have also a higher radial velocity.
Yes, exactly. But the majority of the material is launching in the vertical direction.
Yeah, I would think it involves
exactly.
the balls will be higher. So it's a bit. Okay. Are there any more questions?
We have one message in the
I
chat.
got questions.
Okay.
It's me asking if everybody has questions.
Okay.
So if there are no more questions, we can thank again Alejandro.